If you haven't seen autonomous vehicles cruising the streets where you live, you've probably been hearing about them. They've arrived. Let's talk about the current state of play, what they promise, and how they work. Welcome to the Data in the Story, where we deploy curiosity as our defense and offense in a fast-changing world. I'm CJ Washington. I've been waiting for self-driving cars since I was a kid, so riding in a Waymo was like a dream for me. My wife was adamant that she wasn't putting her life in the hands of AI, and that was fine. The sticking point was our daughter. Go if you must, my wife told me, but you are not taking our child. My daughter pleaded. I pleaded. Finally, my wife relented, and my daughter and I took a Waymo ride. It was awesome. And at the same time, it was surprisingly ordinary. The Jaguar I-Pace Waymo uses is significantly more luxurious than our family car, and my daughter helpfully pointed that out to me. But the ride itself was normal. The acceleration and maneuvers were smooth. Watching the steering wheel turn by itself was kind of weird, but it also added some charm. There's a button you can push to direct the car to pull over, and another button to talk to a human representative. As of this recording, Waymo, owned by Alphabet, the parent company of Google, is providing paid driverless rides in 11 U.S. cities, with plans to expand to more this year. They got their start in Phoenix in 2020 and have since given over 20 million paid rides. In addition, they have a partnership with Toyota to incorporate aspects of their technology into personally owned vehicles. Zoox, an Amazon company, offers free driverless rides in 2 cities. They're supposed to be coming to Atlanta soon, so my daughter and I are looking forward to that. Tesla is testing unsupervised robotaxis in 3 cities, and Uber is making moves. They partner with Nuro, the developer of the Nuro driver, and Lucid, the electric vehicle maker, to deploy 35,000 autonomous vehicles over 6 years starting this year. Self-driving cars are also being tested in Europe, with Waymo announcing plans to expand to London this year. China is a major player with many companies actively involved in the autonomous ride-hailing business. Advocates of autonomous vehicles paint a promising future. According to the Insurance Institute of Highway Safety, roughly 40,000 people died in motor vehicle crashes in the U.S. in 2023. According to the National Highway Traffic Safety Administration, approximately 94% of car crashes are caused by human error. Proponents claim that Level 5 driverless cars could potentially save 1 million lives per year worldwide. That's huge. And then there's traffic. The ability of driverless cars to coordinate with each other and optimize their following distances could relegate traffic congestion to history books. Personally, I won't even read about it. If we can eliminate traffic congestion, I for one will not look back. Some industry experts believe that the adoption of autonomous vehicles will move us away from the car ownership model. They ask us to imagine what cities and suburbs can do with land reclaimed from parking spaces. That's right, we won't need them. A car can drop you off at a restaurant or the movies, and another car can pick you up when you finish. Those paid parking lots can become green space. I can see the appeal of this future, and I'm not sure if I would miss owning a car or not. Not dealing with tires or insurance certainly wouldn't leave a hole in my life. I have a firefighter buddy who loves his pickup truck. I asked him what he thought about trading it in for a ride-hailing plan. He's a man of few words, and his answer was nah. This driverless utopia doesn't appeal to everyone. My daughter is far from driving age, but she's adamant that she wants a license when she turns 16 and a car. I tell her that people used to ride horses to work, and now they ride them for recreation if they choose. Perhaps in the future, car enthusiasts will go to a track. She isn't comforted by this. In the short term, my biggest concern about autonomous vehicles is the impact on jobs. There are about 3.5 million truck drivers in the United States. I personally know parents who drive for Uber or Lyft to make ends meet. Removing those salaries from the economy will impact us all and devastate many of them. According to the New York Times, as part of Waymo's negotiations to enter New York State, Waymo offered to create a $20 million fund to help workers displaced by driverless cars. As of now, Waymo is blocked from the Empire State, but they aren't giving up. Ultimately, The prevailing question is likely to be, who should decide, elected officials or consumers? There are two camps in the autonomous driving world. One camp favors heavy redundancy, detailed maps of the driving area, cameras, radar, lidar. The other camp prefers a slimmed down approach, camera only or perhaps camera paired with radar. The second camp is primarily in opposition to mapping and lidar. They deem mapping too time consuming and expensive. Waymo does not share their mapping costs, but according to Synced, third parties like DeepMap charge as much as $8,000 per mile to create detailed HD maps. And these maps need to be updated to reflect new construction, traffic sign changes, even the addition of bike lanes. Proponents of the vision-only approach also believe LiDAR is too expensive and even ruins the aesthetic of the car. The heavy redundancy camp purports these approaches make the cars safer. Members of both camps tend to be passionate about their approach. Tesla says once they saw vision-only, map-free autonomy, they will scale faster and for far cheaper than anyone else. Waymo says they're currently giving 500,000 safe, paid rides per week, and if the industry changes to vision-only, they will shift with it. We'll talk about mapping, cameras, radar, and lidar, and you can decide which camp you agree with. I'll focus on the Waymo driver, Waymo's name for the autonomous driving technology they've developed. The technology is proprietary, so when I don't know the details underlying the Waymo driver, I'll speak in generalities about driverless car design, but I'll be clear when I'm doing this. According to Waymo, the Waymo driver has driven more than 20 billion miles in simulation. The advantages to driving in simulation are obvious. Engineers can record real-world driving experiences, and in a controlled and safe environment, they can replay the recordings as a simulation and let the autonomous car practice different actions. They can also tweak the simulation, adding pedestrians or changing the actions of other vehicles to test and teach the autonomous car. The Society of Automotive Engineers has defined 6 levels of driving automation. Level 0, no automation. A human handles everything. Level 1, driver assistance. The vehicle might have cruise control or lane keeping assist. The human driver is still very much in control and responsible for operating the vehicle safely. Level 2, partial automation. The car can control steering and acceleration under some conditions, but the driver has to remain attentive and ready to take over at any time. Level 3, conditional automation. The car can handle most driving tasks under specific conditions, but the driver must be ready to take over when the system requests it. Level 4, high automation. This is the Waymo driver. The vehicle can handle all driving tasks, but may have limitations on where and when it can operate. This brings us to the operational design domain, the conditions under which an autonomous vehicle is designed to operate. This includes geographic areas, time of day, and weather conditions. In Atlanta, Waymo operates 24 hours a day, even in adverse weather conditions. Its operations are, however, limited to a 65 square mile area, and it does not drive on highways. Finally, we have Level 5, full automation. This is when humans will no longer need to drive. In fact, if you believe driverless car advocates, we will all be safer if humans don't drive. Before the Waymo driver is unleashed on public roads, Waymo generates highly detailed custom maps of the driving area. Among other things, these maps include speed limits, lane markers, road signs, traffic lights, curbs, crosswalks. They generate these maps by hiring people to drive the streets in cars that image everything. I mentioned that Waymo is a Google company. If you're familiar with Street View, you know that Google is very good at acquiring and deploying detailed, feature-rich geographical data. Autonomy by Lawrence Burns includes the story of how Street View came to be and ties it to the logical next step of developing a driverless vehicle. I'll talk about the book in more detail in a moment. For now, let's explore how autonomous vehicles drive. We can break the process down into a few categories. First, there's route planning. When I ordered a Waymo, I gave it my pickup location and my destination. The Waymo driver uses detailed maps to calculate the best route. To select actions along the route, brake, accelerate, change lanes, turn left, etc., in short, driving, The car needs to do a couple of big picture things simultaneously. It needs to track its location and orientation, called ego-localization, and it needs to maintain comprehensive scene understanding. In terms of a human driver, we would think of this as being aware of our surroundings. Scene understanding encompasses object detection all the way up to predicting the behavior of dynamic objects. When I rode in a Waymo, the area was familiar to me, so I could look around and use landmarks to determine where I was. The Waymo driver accomplishes ego-localization in a similar way. The Jaguar I-Pace is outfitted with 29 exterior cameras, 6 radars, and 5 lidars. The Waymo driver integrates data from these sensors and uses AI to identify and compare landmarks to those on its maps. You might be wondering, as I did, why it doesn't just use GPS. It does, but it can't rely solely on GPS because of reliability issues. The signal can be momentarily lost or corrupted. We've all been on the road when our phone tells us, GPS signal lost. In addition to landmarks and GPS, it combines data from another sensor called Inertial Measurement Unit, IMU. IMUs measure acceleration and angular velocity. Acceleration is change of speed in a direction, and angular velocity is the rate of rotation. If you've ever wondered how your smartphone knows when to rotate its screen, when you go from portrait to landscape, for example, it's because your smartphone has an IMU. IMUs also enable step counting applications. IMUs contain 3 accelerometers, each tracking acceleration along a single axis, up-down, front-back, or left-right, and 3 gyroscopes, each measuring angular rotation along those same axes. Scene understanding comes naturally to human drivers. We rely mostly on vision, but also on hearing. The primary sensors that autonomous vehicles rely upon are cameras, radar, and lidar. Let's dig a bit deeper into each of those. Cameras can be placed strategically around the vehicle to provide 360-degree visibility, and different cameras serve different purposes. A camera with a wide field of view will capture a broad swath of the scene. Because the pixels are spread over a wide area, it's best at providing close-range visual data. A camera with a narrow field of view can provide visual information about objects in the distance, like brake lights or road signs hundreds of feet ahead. Stereo cameras, a pair of identical cameras spaced out on the horizontal axis, like eyes, can be used to perceive depth. The software takes the 2 images, one from each camera, and compares the differences in positions of identical objects to construct a 3D image of the scene. I can always spot Waymos on the road by the large spinning lidar on the roof. Lidar, short for light detection and ranging, emits laser pulses and measures the amount of time it takes for the pulses to bounce off of objects and return, called the time of flight. It uses this time to calculate the distance of an object and to create a 3D map of the scene. Think about the way bats use echolocation. But instead of high-frequency sound waves, lidar uses laser beams. If you think about a beam from the sun, it's composed of visible light of many different wavelengths, from red to yellow to violet, red having the longest wavelength and violet having the shortest. When all of the wavelengths of the visible light spectrum combine, we perceive them as white. A laser beam, by contrast, is made up of light of similar wavelengths. This allows them to stay bright, narrow, and focused. You can't see the laser beams emitted by lidar because they operate in the infrared spectrum. Radar, radio detection and ranging, is similar to lidar, but instead of laser beams, they emit radio waves. The radio waves impact objects and bounce back, revealing the distance, speed, direction, and size of the objects. Of all electromagnetic radiation, radio waves have the longest wavelengths. The specific radio waves radar uses tend to be in the microwave wavelength, which is shorter than those your radio uses, if you like old school tech. Like all electromagnetic radiation, radio waves travel at the speed of light. Now that we have some basic information about the cameras, lidar, and radar that autonomous vehicles use, let's talk about the role each plays in the car's perception. Of the 3 sensors, cameras provide the most detailed appearance information. Cameras capture color, useful at traffic lights, and can be used to read text on signs. LiDAR excels at generating 3D maps of the scene, and radar works even in poor weather. According to Waymo, the radar system can detect and track targets up to 500 meters away. Their cameras can identify pedestrians and stop signs up to 500 meters away. And their lidar can measure the size and distance of objects up to 300 meters away. Lighting and weather are part of the operational design domain, the conditions under which the vehicle is designed to operate. Like our eyes, cameras rely on visible light, which means they share some vulnerabilities with our eyes. They don't work as well under low light conditions, and bright lights can temporarily blind them. While humans are very good at interpreting scenes with shadows, camera systems can have difficulty perceiving where objects end and shadows begin. Radar and lidar don't rely on visible light, so they function well in low light conditions, such as at nighttime or in tunnels. Bright sunlight can interfere with lidar. The photodetectors that detect returning laser beams can also detect other sources of light, creating a noisy signal. It is standard practice to use algorithms to filter out this noise. Cameras, like human eyes, also struggle in adverse weather. Heavy rain, snow, or fog can cause significant performance issues. Laser beams can be scattered or absorbed by rain droplets, so lidar can also suffer reduced performance, but it tends to do better than cameras. Radar excels in bad weather because the large wavelengths of radio waves allow them to pass through water droplets. If you're wondering if radar has any weaknesses, it does. It has lower resolution compared to cameras and lidar, so it isn't as good at detailed object recognition. When you're sitting in an autonomous vehicle, or even when you're sharing the road with one, you're probably more concerned about safety than cost. But I do want to mention that cameras are the most cost-effective of the three sensors, while lidar is the priciest. According to Bloomberg, the full cost for the sensor suite on the Jaguar I-Pace Waymo is about $12,650. I've also seen estimates closer to $9,300. The main takeaway is that these sensors are complementary, and together they provide the car with rich data that is fused and interpreted using artificial intelligence to build a coherent scene. All of this happens in the car's brain. And when I say brain, I mean the onboard hardware, the server-grade CPUs, central processing units, and GPUs, graphical processing units, that run the machine learning algorithms. The Sense-Solve-Go architecture runs fully on board, making each car independent of the cloud. In addition to the primary computer, Waymo cars possess a secondary computer designed to bring the vehicle to a safe stop if it detects a failure in the primary system. As long as that doesn't happen, you can know the Waymo driver is engaged in the hard work of scene understanding, its efforts to maintain situational awareness. Data from its sensors is fused into a three-dimensional bird's eye view of the scene. A neural network classifies objects in the scene, pedestrians, cyclists, stop sign, and localizes them. Is the jogger running on the bike lane or on the sidewalk? That matters for obvious reasons. In this space, you'll often hear the terms semantic segmentation and instant segmentation. These computer vision techniques rely on neural networks. In semantic segmentation, each pixel of the image is assigned to an object category: road, car, pedestrian, sidewalk. If there are 6 cars in an image, the pixel from each car will be labeled car. Instant segmentation assigns each pixel to a distinct object. The pixels in car 1 will be labeled car 1, and the pixels in car 2 will be labeled car 2. The self-driving car also needs to understand the orientation of each object. A pedestrian standing on the sidewalk and facing the road will be regarded differently than a pedestrian standing in the same spot but facing away from the road. If an object is moving, the driverless car needs to track its speed and direction. This is important because the car needs to predict what dynamic objects will do next. During my Waymo ride, we passed a pedestrian jogging in the bike lane. The car veered slightly to the left, giving the jogger space. This might be a pre-programmed behavior. Imagine the angry emails Waymo might receive from runners who feel the car got too close. Or the Waymo driver might have predicted that there was some, probably small, probability that the jogger would veer into the Waymo's path. We didn't encounter an officer directing traffic, but if we had, to understand gestures and intention, the Waymo driver would have employed key point analysis. With key point analysis, the human form is represented with a point for each joint. This representation allows the car to track the pose of the body and understand how it's moving. It can distinguish an outstretched hand signaling the car to stop from a wave signaling the car to proceed. From what I hear, real-world performance is mixed. In addition to image sensors, Waymos are equipped with audio sensors that can detect sirens from emergency vehicles and identify what direction they're coming from. Scene understanding is impressive by itself, but the whole point of perceiving the environment and predicting the actions of others is to allow the car to drive. How do cars learn to drive? Two important concepts are imitation learning and reinforcement learning. In imitation learning, the car learns to drive by mimicking humans. A human drives a car while the sensors detect the state, a complete snapshot of its system and surroundings at a single moment in time. The human driver's actions are recorded along with the state. In this way, massive data sets are created that can be used to train the autonomous vehicle's neural network. The neural network sees a state, integrated sensor data, and predicts the correct driving action, is modeled by human drivers. If it's wrong, the neural network updates its weights to improve the accuracy of its predictions. Hence, the network learns through imitation. This is an effective method, and the car tends to learn the demonstrated scenarios well. But what about dangerous scenarios with a high probability of collision? This is where we turn to a simulator and reinforcement learning. Reinforcement learning involves trial and error paired with rewards. The car drives in a simulation. When it takes a correct action, it receives a positive reward. When it takes an incorrect action, it receives a negative reward. The neural network's weights are updated to maximize rewards, and as a byproduct, good driving decisions. You probably know from reading the news that the Waymo driver struggles on occasion to interpret novel scenes. There's the notorious incident where a Waymo failed to recognize an active criminal arrest. If you have used Gemini, also built by Google, you might be wondering how that could happen. If you upload a photo of police officers with guns drawn pointed at a man lying on the ground, Gemini could tell you exactly what's happening and that you might want to steer clear of it. The problem is that the Waymo driver's neural networks lack a fundamental model describing how the world works. If Gemini could help the Waymo driver, it would, but there are two technical issues standing in the way: latency and hallucinations. Gemini is smart, but it's too slow. But that may not be a problem for long. Waymo was working on incorporating Gemini into the Waymo driver via EMMA, end-to-end multimodal model for autonomous driving. It's still in the research phase. If you're a fan of electric vehicles like I am, you'll be happy to know they provide a superior platform for the demands of the powerful onboard computer. The high-voltage battery supplies the computer's energy needs, while the EV's built-in cooling system prevents overheating. The EV battery can be stored beneath the floor of the vehicle, freeing up space for computer hardware. Also, the brake and steer-by-wire controls used in EVs provide more precision for the driverless car's actuators. The path to autonomous vehicles, though it's still being paved, is a fascinating story. And if you want to learn more, I recommend Autonomy, The Quest to Build the Driverless Car and How We Will Reshape Our World by Lawrence D. Burns. The title says it all. Burns takes us from the evolution of the self-driving car with the 2004 Grand Challenge, a 150-mile off-road autonomous vehicle race sponsored by DARPA, to the implications of the age-old dream of safe and efficient roadways navigated wholly by self-driving cars. He provides a great feel for the personalities central to the development of driverless vehicles. The book was published in 2018, so unfortunately, it doesn't cover Waymo's commercial debut in Phoenix. If you're excited about the progress in autonomous vehicles, you'll be inspired by Burns' vision for the future. If you're skeptical or even hostile to the burgeoning technology, Burns might give you some food for thought. Either way, if you're interested in reading it, you can find a link in the description. If you're interested in a more technical treatment of driverless cars, there are several online courses available. Some of them expect you to have a technical background, and others are open to beginners. We've talked about object recognition, dynamic object behavior prediction, imitation learning, and reinforcement learning. If you're new to AI and you're wondering how this stuff works, I've created a series of 5 primers covering how AI learns. In the first primer, I compare neural networks to the human brain. Neural networks are the foundation of modern AI. The second primer on supervised learning explains the mechanics underlying object classification and imitation learning. The third primer covers reinforcement learning, the technique used to train autonomous vehicles in simulation. The fifth primer covers large language models, LLMs, which just might be the future of autonomous driving. We didn't touch on unsupervised learning in this episode, but the fourth primer is also good, so make sure to check that out. What do you think the future holds? Will we reach level 5 autonomy anytime soon? If so, do you envision safer highways and time reclaimed from driving that can be used to learn new things or maybe even catch up on sleep? Would you like to trade car ownership for a ride-hailing plan? Let me know in comments. Keep your curiosity strong, and whatever you're curious about, I hope it leads you back here and I hope you find what you're looking for. What about other advancements in AI? Do you wonder if they're going to improve your life or just disrupt it? Subscribe, turn on notifications, it's coming. To the data and the story.